Unified dynamics. Distinction theory.
Foundations of modern physics, from the Standard Model to general relativity, begin with a spatial arena already in place. We model the universe within a pre-existing geometric stage, but that stage fractures into a discrete lattice at the quantum scale. Einstein's field equations and current quantum theories depend on smooth manifolds and coordinate systems as unexamined inputs. Geometry is treated as a given rather than a result. Unified dynamics, however, suggests a completely different origin. Spacetime and geometry are emergent consequences of logic, generated from a deeper layer. To find the starting point of physical laws, we have to start before geometry. We have to derive three-dimensional space and matter from absolute nothingness. The process begins with the ground state, U. This is absolute nothingness, a state without shape, particles, or dimensions. This undifferentiated ground state contains a specific logical constraint. In type theory, nothing cannot support a recognition event. For a distinction to exist, there must be a relationship between a recognizer and an object. To satisfy this requirement, the system differentiates into a non-overlapping binary state, A and not A. This split carries an irreducible cost, called the discrete quantum of action, or h-bar sub d. This expenditure prevents the system from collapsing back into a uniform, undifferentiated state. This single distinction triggers a generative sequence. Distinction leads to relation, which leads to closure, and finally to a persistent object. This asymmetric mapping creates the first persistent relational difference in the substrate. It is the minimal structure required to prevent a return to the void. Two isolated points, A and not A, lack stability on their own. They require a formal relation to preserve their distinction over time. This creates a singular transport line, a one-dimensional edge connecting the 2 points. A one-dimensional line links and separates, but it does not enclose a region or self-maintain. The system remains open and fragmented. Stability requires a third node, moving the substrate to level 2 of its development. In topological graph theory, a structure achieves coherent closure when every part relates to every other part, leaving no open ends. Interconnecting 3 nodes forms a 2-dimensional triangle. This is the first minimal community of the substrate, creating an enclosed relational cycle. While 2 points create opposition, 3 points create the first stable relational loop. The system has reached its first level of structural coherence. As the substrate continues to add triangles, the 2-dimensional plane becomes relationally saturated. The connections can no longer expand within the flat surface. The system faces a choice: complete a flat 2D shell by surrounding a center, or escape the plane and lift upward into a new dimension. Adding an apex node forces the system into the third dimension to maintain proximity between all nodes. When all required relations are satisfied, the structure locks. The edges meet, and the system snaps into a stable 3D geometry. This is the K4 tetrahedron. It is built from 4 vertices, 6 edges, and 4 triangular faces. 3-dimensional space represents the lowest dimensional threshold for a stable volumetric interior. It is the minimum configuration required for a physical interior to lock into place. We isolate the K4 tetrahedron because it is the unique outcome of the system's own recursive growth rules. We model this growth as an iterated function system, or IFS, a recursive process that generates complex patterns from simple geometric seeds. Subject to the requirements of topological closure and physical dimension, K4 emerges as the unique fixed point of this growth system. The K4 seed serves as an attractor. It repeats and arranges itself at progressively higher scales, creating a complex fractal lattice. Hutchinson's theorem shows that this recursive process leads to geometric convergence. The discrete network at the small scale dictates the stable geometry at the large scale. The fundamental unit cell of reality is a result of these equilibrium constraints. The substrate's rules allow only this specific structure to persist. Once the K4 geometry is established, it serves as the base node for the next level of physical organization. The 6 edges of the tetrahedron serve as pairwise relational channels. In the continuum limit, As the spacing between these packets shrinks towards zero, the transport values along these edges mathematically converge into the spin connection operator. The four triangular faces provide closure loops. Any failure of the connection to close around these faces creates a measurable curvature defect, mapping directly to the holonomy used in gravitational theory. This bridges the gap between discrete packet interactions and the continuous mathematics of general relativity. Through coarse graining, the dense tetrahedral network smooths out into a Riemannian manifold. The Einstein field equations represent the statistical average of these tetrahedral interactions. They describe the behavior of a network operating in a coarse-grained equilibrium. This same relational lattice generates the standard model. The SU3 times SUQ times U1 gauge symmetries arise from the invariant properties of the network itself. The geometric symmetries of the K4 complex correspond to the directions and behaviors of the fundamental forces. Electromagnetism, the weak force, and the strong force are expressions of different scales of closure and exchange within the tetrahedral lattice. Physical geometry, matter, and fields emerge as companion projections of one underlying relational grammar. We observe a reality built from structural equilibrium, where every distinction endlessly enforces its own persistence.